Hi all, today we'll discuss about today we will discuss about signed magnitude, one's complement and two's complement notation. We all know that in the previous class we discussed that these notations are basically used to represent any number, numeric data. Maybe it is a integer or it is a real value. So these are the three representations. They are signed magnitude, one's complement and two's complement. All of you know that signed magnitude representation basically works on the principle of reserving a particular sign bit for any integer number. Let's take an example. If I have a number called minus 25, then what is its signed magnitude representation means? First take the 25. Already I tell you, you have to apply the weight rule: 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. So just stop the process here. 2 power 4 is nothing but 16. So make a 1 here. So if you subtract 25 minus 16, what happens? Remaining is 19. So this is called 16, 8, 4, 2 and 1. So we already mentioned 1 in 2 power 4 position. So already we completed 16. Now what would be 25 minus 16? The remaining value is 9. So 9 means again I can specify 1 in 2 power 3. So 9 minus 8, how much it would be? 1. So directly I can mention 1 here and 0 and 0. So the binary equivalent of the decimal value 25 would be 1 1 0 0 1. So this is the binary equivalent of 25. Are we able to understand what I am trying to say? So this is very basic rule. This is very basic understanding that everybody must have. Otherwise it is not possible to understand all these concepts. How easily, this is the shortcut. This is a shortcut method for converting a decimal number to equivalent binary number. I'll just repeat the process once again. Take 25. I have to convert this 25 into equivalent binary number. So first write 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. 2 power 5 becomes 32 and 32 is greater than 25. So remove this process. So where we have to stop? When you are go on writing the weights in terms of power of 2, you should know where you should stop. You supposed to stop at a number which would be greater than your desired number, like 25. So if you go on write 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4. 2 power 4 is 16, so I can continue. 2 power 0, 1. 1 is less than 25, continue. 2 power 1. 2 power 1 is 2. 2 is less than 25, continue. Next, 2 power 2. 2 power 2 means 4. 4. So 4 is less than 25, continue. 2 power 3, 8. 8 is less than 25, continue. 6, 2 power 4, 16. 16 less than 25, continue. 2 power 5, 32. 32 is greater than 25, so stop the process here. I hope you are understanding what I am trying to say. So ultimately we should stop the process at 2 power 4. So 2 power 4 means 16, 2 power 3 means 8, 2 power 2 means 4, 2 power 1 means 2, 2 power 0 means 2. Now I should represent this 25. So can I make 1 here? Yes. So if I make a 1, what happens? 25. If I want to represent 25, already I represented 16 quantity by placing 1 here. So if you subtract 25 minus 16, what is the result? 9. Now I have to represent 9. 9 means I can make 1 at 2 power 3 position. So already I represented 8. So what is left? 1. So directly I can say 2 power 0, 1. So the number would be 11001. I hope everybody clear with this concept. Otherwise, it is not possible to understand the ones complement, two's complement. We'll be doing some additions and subtractions over here. So before that, you should know how to convert a decimal number into its equivalent binary value. So 25. So this is the binary equivalent. 11001 is the binary equivalent of the decimal number 25. Now let's assume I want to represent plus 25 in signed magnitude representation. So if you want to represent this in signed magnitude representation, take the magnitude and convert into equivalent binary value and take the sign bit. If the sign bit is plus, mark here 0. If the sign bit is 1, mark 1 here. So 11001. This represents plus 25 and this represents minus 25. So ultimately what's happening here means in signed magnitude representation, MSB. MSB stands for most significant bit. So if these are the number of bits, let's assume 32 bits. This is a 32-bit data. In general, we speak about 64. For simple case, we can take 32. This is called most significant bit. And of course, this is called least significant bit. So in signed magnitude, what's happening? This most significant bit is reserved for signed representation. So we can call it as sign bit. So the sign bit can have two values, 0 or 1. 0 indicates plus sign, 1 indicates minus sign. So 0 indicates plus sign. So in the sign bit place, that is at MSB place, if we have 0, it is a positive number. In the place of sign bit, if the value is like 1, then it represents a negative number. So in case of signed magnitude representation, if I want to do the operations like addition, subtraction, multiplication, division, and but before we discuss that, I hope you remember there are some disadvantages with the signed magnitude representation. One of the biggest disadvantages, I hope you remember, if this is my sign bit, all are zeros, this is also zero. What it represents? Of course, magnitude is 0, 0. But here I have a sign bit. This MSB represents the sign bit. So it is 0. That means it is a plus 0. I hope by this time you might have understood. So in sign bit position I have 1, and this is in case of 5-bit data. Magnitude is 0, so it is 0. But in the place as we have 1 in the sign bit place, it is a negative 0. So there is no uh, in mathematical notation there should not be any sign for 0. 0 should not have any sign. 0 is neither positive value, it's not negative value, it's a neutral. But with this sign magnitude representation, what's happening? It is representing 0 two times, that is plus 0 minus 0, which can lead to some uncertainty while performing arithmetic operations. It can lead to uncertain values, uncertain results when you perform, when we do arithmetic operations, or when computer performs arithmetic operations. Remember, computers is a machine. It should not have any ambiguity. Everything should be unambiguous or clear or certain. So this is the biggest disadvantage of signed magnitude representation. So to overcome this, we have some other representations, and example for such representation is called 1's complement notation. So the 1's complement, as the name specifies, what it says that complement means make 1 as a 0, 0 as a 1. So this is called 1's complement notation, right? So 1's complement notation means make everything as, if you have a number called 1011, this is, let's assume this is one binary number. What is its equivalent decimal value? So its equivalent decimal value is 8421. What are 8421? 2 power 0 is 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8. So here, since at 2 power 3 position we have a 1, 1 into 2 power 3 plus 2 power 2 into 0, 0 plus 2 power 1 into 1 plus 2 power 0 into 1. So 2 power 3 is nothing but 8, 2 power 1 is 1, 2 power 2 into 1 is 2, and 2 power 0 is 1, 1 into 1 is, so the number is 11. I hope you understand this concept. Let me repeat once again. It is because it is very important to understand these conversions. So in the previous slide, just now we discussed how to convert a given decimal number into its equivalent binary value. Similarly, if I give you a binary number something like this, what would be its equivalent decimal value means? So take the binary number 10110, go and write the weights 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4 and 2 power 5. 2 power 5 is 32, so 2 power 5 into 1. Next 2 power 4 into 0, anyway it would be 0, any number multiplied with 0. Next 2 power 3 multiplied by 1 plus 2 power 2 multiplied by 1 plus 2 power 1 multiplied by 1 plus, you need not to calculate. So this 2 power 5 becomes 32, 2 power 3 8, 32 plus 8 plus 2 plus 1, 32 plus 8 40 plus 3, so it is 43. So the binary equivalent of 10110 is nothing but 43. I hope you understand how to convert a given binary number to its equivalent decimal value. So a binary, how to derive a decimal number from the given binary number. If you are clear about this conversion, then we can move further how to discuss how to implement 1's complement. I hope you are understanding this concept of conversion. Now let's move to 1's complement. In general, the meaning of a complement means convert 1 to 0, 0 to 1. It is as simple as that. So, converting 1 to 0 and 0 to 1. 1 means there is a signal at high voltage. 0 means it's not no signal. It is a signal with low voltage. So this is called complement, as everybody know it. And remember, we discussed the biggest disadvantage of signed magnitude is that it is having two zeros. This representation supports two zeros. One is plus 0 and other is minus 0, which is not at all acceptable. So the best solution would be to go for another notation for storing the number in computer's memory. Remember all these notations: signed magnitude, 1's complement or 2's complement notation. All these are the different techniques for storing a number in memory. So let's discuss in detail about 1's complement notation. So in general, the meaning of the complement means a bit with the opposite value to the given one is known as complement in computer science. What it is trying to say, a bit with the opposite value to the given number. Opposite value to the given one. Given one, if it is 0, opposite is 1. The given one is 1, opposite is 0. This is called the concept called complement. Next I have 1's complement. So the 1's complement, I'll give you an example of complement, though it looks basics, but it is very important to understand. Let's assume 1011 is a binary number. If I ask you what is its equivalent complement value, what is its complement value means 0, 1, 0, 0. Are they both equal? No, they are not equal. Are they related? Yes, they are related. In what way? What is the value of 1011? The value of 10, but before discussing the one more example. Let's assume I have a number called 010101. What is its equivalent? It's not equivalent. What is its complement value? 1, 0. In place of 0, I should add 1. In place of 1, I should write 0, 1, 0, 1, 0. It is very simple, right? It is easy to understand the complement. Now, as I said, is there any relation between a binary number and its complement? Certainly there exists. Let's take the previous example, 1011. What is its complement? 0010. To understand the relation between these two numbers, let's convert them into some decimal number and see and try to see or try to figure out, uh, is there any relation exist between these two numbers. Let's find out. So all of you know how to convert this binary number into the equivalent to decimal value, isn't it? Its equivalent decimal value is 2 power 0. You can say 1, 2, 4, 4 and 8. You all know why I mentioned the weights like 8, 4, 2 and instead of 2 power 0, 2 power 1, 2 power 3, right? By this time I hope you understand. Everything is just like converted. 2 power 0 means 1, 2 power 1 means 2, 2 power 2 means 4. Similarly 2 power 3 means 8. So the 8421. So remember this 8421, it's called a weighted code and we will discuss in detail about when we discuss about the codes of a number or alphanumeric data, which is an important topic. So 8421. So now below 8 we have 1, so it is 8 plus I can take 8. Below 4 I have 1, so I can take 4. Below 2 I have 0, so I need not take, don't take, consider it. And below 1 I have 1, yes I can take, so it becomes 13. So the decimal equivalent of 1101 is 13. Yes, 13 base 10. Here of course it is base 2. This is base 2. Now if I convert this, when I convert this 1101 into a complement form, I got another binary number such as 0010, and we can easily identify, right? 2 power 0, 2 power 1, so it is nothing but 2 base 10. So I have 13 here. So when I convert the binary number, the binary equivalent of 13, I got the decimal number 2. Is there any relation between 13 and 2? Can you imagine anything here? Yes. see what is the maximum number, or what is the biggest number, what is the largest decimal value that you can represent with 4 bit binary value or 4-bit binary number. To discuss that, you should understand certain things which I will mention now, which are very important. I said 4 bits, right? Remember, if these are my 4 bits, if I put all zeros, this is the smallest positive number, and if I keep all ones over here, it is 15. Do you understand why the all ones means 15? Just apply the rule, weighted rule, 8 4 2 1. So 8 has 1, 4 has 1, 2 has 1, and 1 has 1. So 8 plus 4 plus 2 plus 1, that becomes 15. So the maximum unsigned number that you can represent using 4 bits is 15. Now I have a question for you. Can you guess or imagine, can you derive what is the smallest signed integer and what is the largest signed integer that you can represent with 4 bits? I'll give a hint for you, then you can work it out as an assignment. Okay, and when I say signed bit, all of you should know that the MSB bit is reserved for signed bit. So if I keep 1 here, and if I keep all ones here, what would be this number? 1 2 4. I should not write 8 because this is reserved for sign in case of signed integer. Since it has 1, the number is minus. You all know that if a sign bit value, if the value of a sign bit is 1, then it represents a negative value, negative quantity. Similarly, if the uh, sign bit has 0, it represents a positive value. So this, in this case, I have negative number, negative, and 1 means 4 plus 2 plus 1, of course, minus 7. And if I have a 0 here, minus 7 to plus 7. So this minus 7 is the smallest negative number or smallest signed number that you can represent with 4 bits. Similarly, plus 7 is the largest positive number or signed number that you can represent with 4 bits. Now, when this rule is applicable, if your representation is a signed magnitude. Now, I will give an assignment. If I have n bits, can you imagine, can you guess what would be the smallest number that you can represent, smallest signed number, and the largest signed integer? Just correlate with 4 bits. In 4 bits, if you say 2 power 4, 16, right? If you make 2 power 4 minus 1, 8. Again minus 1, 7. So minus 2 power 4 minus 1, 2, plus 2 power 4 minus 1 minus 1. I don't know whether you are really understanding or not, but this is very important in terms of 1's complement, 2's complement notation. So largest, so if I have 4 bits, The largest number is 1, 1, 1, 1. How 1, 1 comes? 2 power 4 is 16, minus 1 is 15. 15. It's an unsigned representation. It is quite simple. But the difficult part is when you have 4-bit signed value, 4-bit signed integer. So what is the largest value means? Here I have, in place of, when it comes sign concept, this is called sign bit, and this sign bit will have 1, 1, 1. 1, 1 means, the sign bit means, you know that minus 7 to plus 7, 4 bits. So I should derive a formula using, so if n is equals to 4 minus 7 to plus 7. So how can I derive from 4 to this minus 7 to plus 7? It is important from competitive exam point of view. Minus 7. So minus 7 I can write it as, I should take the input as 4. 2 power 4 minus 1. How it would be? 2 power 4. 2 power 4 minus 1. 4 minus 1 is 3. 2 power 3 is 8. But I should get 7. So subtract 1 over here. Negative sign. 2 plus 2 power 4 minus 1 minus 1. This is the formula. So if I generalize this formula for any particular n value, then how I should write means, let's assume for n is equals to k minus 2 power k minus 1 minus 1 to plus 2 power k minus 1 minus 1. It is so simple. I hope you understand. Remember this formula. It is very important from competitive exam point of view. Now, 1's complement, subtraction of a binary numbers. So this complement concept, 1's complement concept comes when I have to do subtraction. See, for doing addition, I need not to have 1's complement. So basically you should understand that 1's complement or 2's complement representations are used to represent a negative number. For representing a positive number, you need not to have complement notation. Signed magnitude is enough. But remember, this 1's complement notation or 2's complement notation comes into the picture when you want to represent a negative number or when you go for subtraction. Why? If I say a minus b, if I have to do a minus b, can I write like a plus of minus b? Yes, I can, because plus multiplied by minus again would become minus. There is no difference. So ultimately what I am trying to do, I am converting subtraction into addition. So this is an important. So it is required to represent minus b. Minus b is a negative number. So if you want to represent a negative number, you should use 1's complement or 2's complement. So this is the meaning of subtraction of binary numbers, like a minus b. Subtraction of, if a is a binary number, b is another binary number, a minus b. Subtraction of the binary numbers using the 1's complement method allows the subtraction only by addition. So just now I discussed. So using 1's complement method, what happens? I can convert this subtraction into addition. How? I can write a minus b as a plus of minus b. If I represent minus b in 1's complement method, it just becomes an addition. So you should understand the relation between a complement and a binary number. The complement of 1101 is 0010. This is 13. This is 2. If you sum up this 13 plus 2, 15. 15 is the biggest number that you represent with 4 bits. So the complement of a binary number is nothing but you will get a complement of a number by subtracting the maximum value, maximum unsigned representation with those number of bits. This is the relation between a number and its 1's complement. I hope you understand this point. Next, I have to subtract a smaller number from the larger number. The 1's complement method is as follows. That means if I have to subtract the smaller number from the larger number, I have to follow this method. 1's complement I can do. How? So let's take an example mentioned over here. Now I have to subtract 1010. Can you guess what is the decimal equivalent of 1010? 2 power 0 is 1, 2 power 1 is 2, 2 power 2 and 2 power 3. 2 power 3 is 8. 8 into 1, 8 plus 2 power 1, 2. So the number is 10. So subtract 10 from, of course, all 1 means 8, 4, 2, 1. 8 plus 4 plus 2 plus 1 means 15. So I have to subtract 15 from 10. This can be done even by a kid, but if the same thing wants to be done by a computer, see how it follows the technique. So this is 10, this is 15. Subtract 10 from 15, so you get 5. The answer should be 5, isn't it? Okay, let's see how it works using 1's complement. So here let's assume this is b, this is a. The goal is convert a minus b as a plus of minus b. So minus b means 1's complement of b. And this is another important thing that you should remember. Complement of a b is nothing but minus b. So a plus of minus b. Let's see the calculation. So the direct subtraction, what it says, if you follow the subtraction rules, 1 1 1 1 1 0 1 0. If I subtract 1 minus 0, 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 1 is 0. So straight away I am getting 5. But this is the manual procedure. The computer wants to do the same thing. If the computer wants to do how it follows means, if it follows 1's complement method, so it takes the number 1111 because I have to convert 15 minus 10. So 15 plus of minus 10. Minus 10 means complement of 10. By this time you should get that complement of 10 is equals to 5. How? Can you guess how the complement of 10 would be 5? Because the maximum 4-digit number is 15. 15 minus 10 is nothing but the complement of 10, that is 5. So 5. Or you can say that the complement of 1010. You can verify this. Say the complement of 1010 is 0101. That is 5. Right? So 0101. 15 plus 5. What happens? You would get result You have to do addition. 1 1 1 0 1 1 1 0 1 1 1. So you are getting the result as 1. So you are getting 1 0 1 0 0. So the concept, I hope you are understanding. So when I do addition 1 1 1 1 using 0 1 0 1, I am getting 1 1 is 0, 1 plus 1 again 0, 1 plus 1 plus 1 is 1 1. So I am getting 0, and I am getting a carry over here because it's a 20. I can't represent with 4 bits. Definitely I will get carry. So just what is the result? 4. The result is 4, but I should get 15 minus 10 as a 5, not 4. So what I should do? Add this carry. Simple. 0 1 0 0 is the result. Add carry, you will get 0 1 0 1. It is nothing but 5. It is as simple as that. I hope you are understanding. I hope you are understanding this concept. So this is the way of subtracting a number from here. The logic is you are subtracting the smaller number from the bigger one. So you should remember that when you subtract the smaller number from the bigger one, you should get a carry. When you get a carry, just you have to add the carry to the result, and you will get the final result. This is very simple. Can we do this conversion in decimal? See, 15 minus 10 means 15 plus half minus 10. 15 plus half. So what is the complement of 10? 5. So I should get 20. This is not happening in decimal, but the same thing you can do in binary number. So this is the procedure. Mommy. Daddy.